Scene script. Have you ever wondered how the air we breathe, an invisible gaseous substance, can be transformed into a liquid? Well, you're about to find out. In the world around us, matter exists in three primary states: solid, liquid, and gas. Each state has its own unique properties. Gases, for instance, are fascinating because they have the ability to fill any space or shape. They are like the ultimate chameleons of the natural world, constantly adapting to their surroundings. But what if we told you that these shapeshifters can change their state altogether? Yes, gases can actually become liquids. This might seem like a magic trick, but it's purely science, and the process is known as liquefaction. Liquefaction of gases is an intriguing phenomenon. It's like a superhero changing their disguise. But instead of a cape and mask, gases use cooling and pressure as their tools of transformation. When gases are cooled or compressed, their particles slow down and get closer together. This results in a phase transition from a gaseous to a liquid state. Imagine having a bag full of bouncy balls. When the balls are bouncing around, they represent a gas. But as soon as you start squeezing the bag and make the balls come together, they begin to represent a liquid. Just like that, gases can be squeezed into becoming liquids. But how exactly does this happen? What's the science behind it? There are two key processes that make this transformation possible: Linde's process and Claude's process. These are named after the scientists who developed them, and they are the unsung heroes in the world of gas liquefaction. Now let's dive deeper into the intriguing processes that make this transformation possible. Imagine being able to squeeze air so much that it turns into a liquid. Sounds impossible, right? But that's exactly what Linde's process does. Now let's unravel the science behind this fascinating phenomenon. Linde's process, named after Carl von Linde, a German scientist, is a technique that's all about the compression, cooling, and expansion of gases. Picture this. You have a gas. You apply pressure to it, making the molecules huddle closer together. This is the compression phase. The gas is now at a high pressure, and the molecules are feeling the heat, literally. They've been squeezed together so much that the gas's temperature rises. Now we need to cool it down. In comes a cold substance, perhaps something like chilled water. This substance absorbs the heat from the gas, cooling it down. This is the cooling phase. But we're not done yet. The gas is now cool and compressed, but it's still a gas. The final step is to let the gas expand. As it expands, it cools down even more. So much so that it crosses that magic line between being a gas and becoming a liquid. This phase is called expansion, and voila! You have a liquid that was once a gas. This process is often used in industrial settings to liquefy gases like oxygen, nitrogen, and argon. It's like magic, but it's not. It's science. The Linde's process takes advantage of the Joule-Thomson effect, which states that when a gas expands, its temperature drops. So by compressing a gas, cooling it, and then letting it expand, we can effectively turn it into a liquid. That's Linde's process for you, a marvelous scientific method that turns airy gases into tangible liquids. The beauty of science is that it often defies what we think is possible, transforming the invisible into the visible, the intangible into the tangible. It's like pulling a rabbit out of a hat, but instead of a rabbit you get a liquid, and instead of a hat you have a gas. It's not magic, it's Linde's process. Now imagine a process that not only liquefies gases but also makes them super cold. Welcome to Claude's process. This ingenious method, named after Georges Claude, a French engineer and inventor, is a step up from Linde's process. It's like Linde's process on a caffeine rush, taking the concept of gas liquefaction and supercooling to an entirely different level. So how does it work? Well, let's break it down. In the Claude process, the gas is first compressed. This compression causes the gas to heat up, but we don't want that, do we? So we pass the warmed gas through a cooler to bring its temperature down. The cooled gas is then allowed to expand partially in an expansion engine, causing it to lose even more heat. But wait, there's more. The gas, still in a high-pressure state, is then passed through a heat exchanger where it cools down the incoming gas. The outgoing gas is now super cold and in a low-pressure state. It's then expanded further in another expansion engine. This final step of expansion causes the gas to lose more heat, and voila, it liquefies. The brilliance of Claude's process lies in the additional expansion engine. This extra step allows for further cooling and liquefaction, which makes the process more efficient than Linde's. It's like having an extra gear on your bike that you can shift into when you need that extra push. The additional expansion engine in Claude's process is that extra gear, giving the process the extra push it needs to get those gases super cold and in their liquid state. And there you have it. Claude's process, a fascinating and complex method that takes gas liquefaction and supercooling to the next level. It's a testament to human ingenuity and our quest to understand and manipulate the world around us. And that's Claude's process, a fascinating technique that takes gas liquefaction to a whole new level. Ever sprayed deodorant or used an inhaler? You've unknowingly used the principles of gas liquefaction. This fascinating concept plays a crucial role in our day-to-day lives, particularly in the realm of aerosols. Aerosols are suspensions of tiny particles or droplets in a gas. They're not just limited to your deodorant or hairspray, but are also present in natural phenomena like fog and dust storms. However, for these everyday products to work, the gaseous components need to be liquefied, and that's where the magic happens. The principle of gas liquefaction in aerosols is achieved through two-phase and three-phase systems. In the two-phase system, the product consists of a gaseous phase and a liquid phase. The gaseous phase is typically a propellant, a gas that helps to spray the liquid phase, which is your product, out of the can. The liquid phase is kept under pressure and is liquefied. When you press the nozzle, the pressure is released, causing the liquid to rapidly convert back into a gas. This sudden gasification forces the product out of the can in a fine mist. In the three-phase system, things get a bit more complex. Here we have a gaseous phase, a liquid phase, and a solid phase. The solid phase is usually a suspension of tiny solid particles in the liquid. The gaseous phase, once again, is the propellant. When the nozzle is pressed, the propellant gasifies, pushing out the liquid and solid phases in a fine spray or foam. This is often used in products like whipped cream or foam-based fire extinguishers. So these processes aren't just scientific marvels, but they're also incredibly practical, permeating through various facets of our lives. From personal care products to medical applications and even fire safety, the principles of gas liquefaction and aerosols have a wide range of uses. So the next time you use a spray can, remember the amazing science that makes it all possible. So, we've traveled from the world of invisible gases to the realm of tangible liquids, all thanks to the power of science. Let's take a moment to dive back into the fascinating journey we've just been on. We started our exploration with the mystery of gases, those invisible particles that are all around us, explaining how their characteristics allow them to exist in a state that is both elusive and omnipresent. Then we moved on to Linde's process, a brilliant scientific method that uses the principles of pressure and temperature to transform gases into liquids. We delved into the intricacies of this process, how it utilizes the Joule-Thomson effect to cool and condense gases, and the crucial role it plays in industries such as air separation and natural gas processing. Next stop was Claude's process, another ingenious method of gas liquefaction. We discussed how this process, unlike Linde's, uses external refrigeration to achieve the desired cooling effect. The importance of Claude's process in the production of liquid oxygen and nitrogen, essential for many modern technologies, was also highlighted. Our final destination was the world of aerosols, where we saw the application of liquefaction in real time. We learned about the principle of aerosols, how these tiny liquid droplets or solid particles suspended in a gas play a vital role in various fields, from medical treatments to climate studies. We examined the nuances of two-phase and three-phase systems and their role in creating effective aerosols. In essence, our journey from gases to liquids has been a testament to the wonders of scientific innovation and the boundless potential it holds for the future. It's a reminder that the world of science is as vast as it is intriguing, and there's always something new to discover. Remember, the world around us is full of fascinating science, and all it takes is a little curiosity to uncover it. Subscribe for more because you won't find me later.